This section covers exceptions. An exception is an event that disrupts the normal flow of the execution of your code. The exception routine is a special piece of code that tries to figure out what is wrong by checking the status of the CPU, seeing if it can be corrected, and then continuing along, executing the normal code like nothing happened. Here are some of the most common causes of an exception. An interrupt is caused by a device that is external to the CPU, for example, a clock interrupt or a packet of information coming from the network. Another common cause is a TLB miss, and the exception needs to update the TLB with the proper translation. A floating point exception, which happens when the CPU doesn't know how to execute an instruction that has been given. A program or hardware detected errors. Most of the time, these are problems with the execution of an instruction. For example, these exceptions happen when user mode process tries to execute an instruction that can only be executed in kernel mode. Sometimes a programming error can cause a code area to be overwritten with data, so the instructions in that area are now garbage. So when the CPU tries to execute this code, it will generate this exception. If your cache is designed for it, the cache can generate an exception when the CPU accesses a cache instruction or data and there is a parity error that isn't been corrected. A system call is a way for a user mode program to transfer control to an OS running in kernel mode, usually to request an OS service, for example, writing data to a disk drive. There are more exceptions. Consult the Software User's Manual for your core for a full list. Determining where an exception happened can be an issue. You may need to know what instruction caused the exception to be able to fix it, and also you need to know where to restart normal execution. Most of the time the CPU can tell precisely what instruction you are executing, so you can determine what happened and where to restart normal execution. These are called precise exceptions. When a precise exception happens, you can be sure that all instructions in the execution stream before the exception is reported have been executed. On return from exception, the CPU will restart execution with the instruction that was set to execute at the time the exception happened. Do not cause any ambiguous executions. Instructions in a branch or jump delay slots are paired with the branch or jump. The return from exception execution will always execute the branch or jump, even if the exception happened due to the instruction in the delay slot. There are times when the CPU cannot precisely determine what instruction caused the exception or where to restart execution. It can only tell you what instruction was executing when the exception was detected. A bus, cache, and L2 cache errors can be one of these exceptions because the load is non-blocking and allows other instructions to be executed until an instruction tries to execute that is dependent on the data being loaded. So the bus error for a load can occur on another instruction. A fetch can cause a bus error, but since most cores fetch ahead of execution, the bus error may also happen while executing another instruction. Only reads from the bus can cause bus error exceptions. With that in mind, you may think that a store could not cause a bus error exception. It is after all a write to memory. However, stores to cache memory can indirectly cause bus errors. When data is being written to the data cache and there is a cache miss for that cache line that contains that data, the cache controller will request a read of an entire cache line from a line of memory. It will then merge the word being stored. This read from memory can also be the source of a bus error. Most of the time, this is where things go terribly wrong. Recovery from these errors can be tricky. First, you need to correct the error or try the bus operation again. Unless you have designed your code to checkpoint itself, as it goes, so you can determine a good restart point. It will be hard to do anything but restart the entire process. Most of the time this will fail in the same place, and you'll be left with trying to report the problem to the user. There is a special error condition for reset, NMI, and cache errors called error level. You can tell if the CPU is in this state by checking the ERL bit in the status register. The ERL bit is bit 2 of the status register. When this bit is set, the CPU is in kernel mode and all interrupts have been disabled. The reset and NMI exception vector is usually BFC C00000 hex. The cache error exception vector is different depending on the boot exception vector bit in the status register. If the boot exception vector bit is set, as it is at boot time, then the cache error vector is BF C00300. If it is not set, then the vector is A0000100. The idea here is that you may take a cache exception when you are booting from ROM or flash, but once you have initialized your system, you can clear the boot exception vector bit and the cache exceptions will go to a faster memory. The A0000100 vector is still, of course, in uncached region of memory in KSEG 1. One thing to note is the memory map changes when the ERL exceptions happen. The main concern here is for a cache error. The cache might get an ECC error which might be software correctable. When that happens, the CPU takes a parity ECC error exception with the boot exception vector bit set. This is handled separately from a standard exception because a correctable ECC error can happen anywhere, even in the most sensitive part of another exception routine. So your cache exception handler must be able to fix them regardless of when they occur. The trick is, how do you do that when there are no registers you can safely use, not even as pointers to start saving register values? To solve this issue, when the cache exception vector happens, the ERL bit gets set and the memory map changes. All access to normal user space translated addresses disappear. The program address from 0 through 7FFF become direct mapped and uncached. In this state, the cache error exception handler can use base plus offset addressing to offset the 0 register to access uncached memory space, which needs to be reserved by the OS for this purpose, to save registers and make itself room to run. The ERET instruction will use the return address held in error PC instead of EPC in this case. The exception level bit in the status register is set by the processor when any exception other than reset, soft reset, NMI, or cache error exception is taken. The EXL bit set means that the CPU is in normal exception mode, set to process an exception that can be returned from using the exception program counter or the EPC. In this mode, the exception program counter contains the program counter that the CPU was processing when the exception happened. Also, there is a bit called the branch delay bit located in the cause register that will be set if the CPU was executing an instruction in a branch delay slot. The exception code should be used to determine which instruction might have caused the exception. If the branch delay slot bit is set, either the instruction at the exception program counter or the instruction in the branch delay slot could have caused the exception. All interrupt exceptions, both software and hardware, will be disabled by the CPU before execution of the exception routine. Exceptions other than interrupts can still occur. Note, the exception PC cause register's branch delay slot bit and the shadow register set's control bit will not be updated if another exception is taken. The eBase register is a read-write register containing the base address of the exception vectors used when the status register's boot exception vector bit is 0, which the boot code can clear once it has initialized the cache and is ready to use cacheable vectored addresses. It also contains a read-only CPU number value that may be used by software to distinguish different types of processors in a multiprocessor system. Bit 31 is hardwired to force all vectors into the cacheable KSEG0 address space, with the exception of the cache error exception, which will be forced into the uncached KSEG1 address space. Bits 12 through 29 work in conjunction with bits 31 and 30 to specify the base address of the exception vectors. Bits 11 and 10 are reserved bits and must be written as zeros. They will always return zeros when read. Bits 0 through 9 are usually set when the processor is implemented with a unique value to distinguish one processor from another. Your code can use this to determine which processor it is dealing with. Bits 0 through 11 do not figure into the exception base address. Let's take a moment to review what I have talked about so far by using a table of exception vectors. The first vector is commonly called the boot exception vector because the CPU at PowerUp will always start fetching its first instruction at this vector. This vector is also used for reset, soft reset, and non-maskable interrupts. All of these will cause the system to reboot. As a reminder, the vector BFC00000 hex is in a non-cacheable KSEG1 address space, which is directly mapped to physical address 1FC000 hex. The next two sections of the table will depend on the boot exception vector bit in the status register. The boot exception vector bit is set on cold boot. Usually your system will have a boot ROM or flash RAMs that occupies some of the memory that is located at the boot exception vector physical address of 1FC00000. Remember, that's virtual address BFC00000. The range of this ROM or flash will run at least through the address range of the exception vectors shown here and the area needed for the boot code. The boot code starts at the boot exception vector and initializes the cache and the TLBs and sets up exception routines in the cacheable KSEG0 address space. There will be more on boot code in the boot section of this course. Once the boot code is done enough to be able to use KSEG0, the boot exception vector bit is cleared. Aside from the cache exceptions, any exception that come after this will go to their cacheable address in KSEG0. The cache vector changes but remains in the uncached KSEG1 address space. Last, there are special vectors for use when the CPU is implemented with the EJTAG tap controller. The address segments in red can be altered by use of the exception base register eBase. I will cover interrupt exceptions in detail right after I talk briefly about general exceptions that use the general exception vector. General exceptions are any exception that are not external interrupts, TLB refills, cache, NMI, or resets. All general exceptions go to the general exception vector. To determine which general exception has happened, the code must be examined in the exception code field of the coprocessor 0 cause register. Let's talk about some of the more common general exceptions. A TLB refill is normally handled by a special exception vector, the TLB refill vector at 80 million hex. In cases where the CPU gets a TLB miss while already trying to handle a TLB refill, that second exception will go to the general purpose exception vector. More detail on the TLB exceptions are covered in a separate course segment on the TLB. A machine check exception happens when duplicate entries have been written to the TLB. If this occurs, the exception routine needs to read all the TLB entries and overwrite or invalidate the duplicate entries. A watch exception happens due to an instruction or data access that matches the address specified in the watch registers. Watch exceptions are not taken if the CPU is already in exception mode. Instead, these watch events are remembered and result in deferred watch exceptions, which is taken as soon as the CPU leaves exception mode. An address error exception is taken when a load or store tries to access data that is not aligned to a data type of the instruction. For example, the destination address of a store half-word instruction must be aligned on a half-word boundary. An instruction fetch from a non-32-bit aligned address for normal instruction or a 16-bit address for a MIP16 instruction can also cause this exception. This can also happen if the EPC or EPC register were overwritten with an unaligned address. Any reference to kernel address space while the CPU is in user mode can also cause this exception. A bus error is generated by an external device when there is a problem in completing a memory request. A system call instruction is coded into your program by the compiler when your program references a function that needs an OS service. For more information on a system call instruction, refer to the MIPS instruction set section of this course. A reserve instruction exception can happen if there is an instruction that the CPU cannot execute. This can be by design in the case of a floating point instruction that is intended to be handled by software, or it can be due to a corrupted code section. Coprocessor unusable exception happens when the CPU tries to execute a coprocessor instruction for a coprocessor that is not enabled, or when it is in user mode and tries to execute a coprocessor 0 instruction. Core extend unusable exception happens when the core extend enable bit is not set. Core extend instructions are user-definable instructions that are incorporated into the CPU design. The core extend enable bit offers a programmatic control over the use of these instructions. For example, in a virtual processor core such as a 34K, these instructions can be limited to one of the thread processing units, so the other units would cause an exception if it tried to execute a core extend instruction. Floating point exceptions are any exception raised by the floating point unit. You will need to examine the status of the floating point unit to determine the cause. Integer overflow instructions happens on selected instructions when the result overflows the size of an integer. The trap instruction is raised when a trap instruction results in a true condition. The MIPS instruction set section of this class has more information on trap instructions. The TLB modified instruction is caused by a TLB valid entry that is referenced with the dirty bit cleared. The TLB and the use of this bit is discussed in the TLB section of this class. A breakpoint exception is caused by an execution of a break instruction. The MIPS instruction set section has more information on break instructions. For additional exception information, consult the Software User's Guide of your core. Now I'll go into more detail on interrupts. Interrupt exceptions are generated by external events. There are three ways the CPU can handle these events. First, all interrupts can use the general exception vector. In this case, the exception routine would check the exception code in the cause register and see that it was an interrupt exception. Then the code would check the status of each device to see which one caused the interrupt. This is commonly called interrupt compatibility mode because it is the only way interrupts can be handled on very early MIPS processors and is still available, so code written for them will still work on more current processors. The second way the CPU can handle interrupts is the use of interrupt vectors. The CPU has 6 external interrupt pins that can be wired to devices so that they can signal the CPU when there is an interrupt. Each pin is associated with a program vector. When the CPU detects which pin is causing the interrupt, it starts executing at that vector the pin is associated with. Sometimes there is more interrupt sources than 6, so some devices may be wired to the same pin, and when the interrupt comes in, the code needs to query the device so that it knows which one caused the interrupt. The highest pin number is given the highest priority. And third is the external interrupt controller mode, or EIC for short. An external interrupt controller can supply the CPU with a value from 0 to 63. 0 indicates that there are no interrupts pending, and 1 through 63 indicates the vector of the interrupt to be serviced. So in this mode, the CPU can be given 63 different interrupt vectors. Interrupts that use the general interrupt vector are pretty easy and handled like any other exceptions. Using the one general interrupt vector for interrupts is not much used because it offers the poorest performance in interrupt handling. It's really only there for compatibility with older code, and I don't advise using it for new projects. I'll now go into how vectored interrupt mode is used. To enable vectored interrupt mode, the boot code needs to set the interrupt vector bit number 23 in the cause register. While we're here, I'd like to point out the interrupt priority bits. These bits will give you status on what interrupts are active. You can check these bits at any time for pending interrupts, although you don't need to do so for normal operation. The interrupt priority bits are made up of 6 hardware pins and 2 virtual software pins. The software interrupts are tied to virtual interrupt pins 0 and 1 and are the lowest priority interrupts. The idea behind them is that you can use these software interrupts to complete interrupt processing that doesn't need to be done at a higher level. So you can be processing an interrupt, say, at level 5. Your code takes care of all the critical things, but has some additional cleanup to do that doesn't need level 5 priority. You can raise a software interrupt that will trigger a software interrupt after all pending and enabled hardware interrupts have completed. You can do this by setting the virtual software pins bits 8 or 9 in the cause register. You can use the interrupt mask bits in the status register to control which individual interrupt pins will be enabled by the processor. When an interrupt pin is raised by an external device, it will cause the CPU to start the interrupt routine only if the corresponding bit in the interrupt mask field is set. The interrupt vectors start at address BFC00400 during the boot process when the boot exception vector bit is set, and at 80000200 during normal operation when the boot exception vector bit is cleared. In both cases, this address is after any other exception vectors. Where the code for the next interrupt vector starts is programmable. You can select how much room there is between vectors. Usually, there is just enough room for you to set up the interrupt stack, save registers as needed, and call a C function to do the rest of the interrupt processing. But you can have up to 512 bytes for code in between vectors. Note, there is only one setting that applies to all interrupts. The setting of the vector spacing is done by using the vector spacing bits in the CP0 interrupt control register. The boot code should set up this spacing before interrupts are enabled. You will see an example of this later in this section. If you have viewed the MIPS instruction set section of this course, you know that there are two instructions that make interrupt control easier. I think it's a good idea to go over them here again. First is the disable interrupt instruction. This instruction helps by atomically saving the current value of the status register to a general purpose register and clearing the interrupt enable bit in the CP0 status register. The interrupt enable instruction automatically saves the value of the status register to a general purpose register and sets the interrupt enable bit in the status register. Note, you might not always want to use the interrupt enable instruction, particularly if you are nesting interrupts. You might just want to restore the status register with the value that it had when you entered your interrupt function. So the interrupt enable bit in the status register will remain as it was, and the CPU will continue processing any lower priority interrupt function that it may have interrupted. The boot code and interrupt handling code will need to enable interrupts. To do so, the code needs to make sure the following bits are set correctly. The error level bit is cleared. The exception level bit is cleared. The interrupt enable bit is set. And the debug mode bit is cleared in the CP0 debug register. Next, the code must enable individual interrupt vectors by setting the corresponding bit in the interrupt mask field of the CP0 status register. Before I go into a specific code example, I want to give you an overview to make it clear about what happens through the interrupt process. First, I'll start with what the CPU does. Once an interrupt pin is raised, and that pin is not masked off in the status register, the CPU sets the exception program counter to the restart address where normal processing should restart. It sets the EXL bit in the status register. This has the effect of switching the processor into kernel mode and disabling all interrupts. The coprocessor 0 cause register is set to indicate the interrupt state. For example, the interrupt priority bit in the cause register is set for this interrupt source, and the exception code is set to indicate the cause of the exception. If this were an exception, you would have to consult the exception code field in the cause register to determine what exception happened. If this were a vectored interrupt, you would already know the cause was an interrupt, so you wouldn't have to check the exception code field. Also, if the CPU is not using vectored interrupts, the vectored interrupt bit in the cause register is cleared, and there is no enforcement of interrupt priority. Your code can dictate which interrupt can be serviced first by checking the interrupt priority field of the cause register and selecting a pin to service. It would be best to stick to the priority scheme of the highest pin being the highest priority, but you don't have to in this mode. The CPU then fetches the first instruction at the associated interrupt vector. Before I go into the actual code example, I'll give you an overview of what your exception code should do. When exceptions are disabled, you can use the general purpose registers K0 and K1 without saving them. Save the mask bits in the status register. The easiest way would be to save the whole status register. Change the mask bits to mask out any interrupts of the same or lower priority than the one being serviced. If the rest of your interrupt routine is in C, you must first make room on the stack to save all of the general purpose registers and then save them. If you are using a shadow register set for this vector, you won't have to save the general purpose registers, but you will need to make a copy of the stack pointer and the global pointer to the shadow set. If you are going to allow for nested interrupts, you will need to change the CPU state. Enable interrupts by setting the interrupt enable bit in the status register. Set the kernel mode by clearing the user mode and supervisor mode bits in the status register. That way, when you leave the exception level, you will still be in kernel mode to process the rest of your exception routine. Leave exception mode by clearing the exception level bit EXL in the status register. Now you can jump to your C function. On return, you will need to disable interrupts again so you can restore the pre-interrupt values of the registers and resume execution of the interrupted task. You can do this by restoring the status register with the copy that you saved off in the beginning of the interrupt routine. Make sure that the interrupt has been acknowledged and cleared on the device that caused the interrupt. Restore the CPU state so the interrupted code can continue unchanged. Restore the general purpose registers. On a side note, since you saved all the general purpose registers, this step will restore the stack pointer and the global pointers of the interrupted code, so you shouldn't use the stack and global variables that are dereferenced using these registers after this step in your interrupt code. Now you are ready to return from the interrupt exception. The code needs to jump to the address in the exception program counter and enable exceptions. You should use the ERET instruction to do this because it will atomically clear the EXL bit in the status register and jump to the address stored in the exception program counter. I am going to show you an example of an interrupt. For this, I'm going to use a simulator that has a timer interrupt source. The code itself goes into extremes to give you a complete example that will pertain to most interrupts. So keep in mind, if you are doing just a timer interrupt, the code could be much smaller. I will use our Navigator ICS product to debug and run this example in the MIPSIM simulator. I'm going to go through the files that make up this demonstration, and I will talk about each one individually afterwards. Common.h is an include file that defines the common register names. You can also find these definitions in mips/regdef.h. Start.s is simple boot code to show you how to set up the CPU for interrupts. ISR.s contains the actual interrupt code that is placed in memory at the interrupt vector addresses. This will show you how to write the assembly code part of the interrupt, and along with the linker file, how to build the code so it will be placed in the proper locations in memory. Main.c is just a simple program to exercise the interrupt. Link.ld shows you how to place the code in the correct memory addresses. The makefile is a simple makefile to build the project. Common.h contains common register defines, so the assembly code can use the register names of the general purpose registers instead of the register number. ISR.s contains the code that will be placed in memory to correspond to the interrupt vectored addresses. This file contains the code for the two functions I will be showing you. The rest of the functions are just stubs to be associated with unused interrupt vectors. These will just do an ERET instruction to return from the interrupt. Link.d uses the .section directives of the ISR.s source file to link the code to each interrupt routine to their vector addresses. The main.c function contains a function that initializes a global array that will be used by the interrupt function to count the number of times it has been invoked. Then the main function will go into a loop counting the number of loops. There is also a simple C function that will be called from the interrupt routine. The function will increment an element in a global array depending on the argument to the function. The make will build the system. You can also use an all dump argument to the make command that will also create an object dump of the executable. Start.s contains code to initialize the interrupt processing and jump to the main function. I will now cover the start.s file that initializes the interrupts in detail. One of the first things you will see in the start.s file is the .set no reorder. This is done because I want to control what goes into the branch delay slots of the assembly code. The next piece of code will enable vectored interrupt mode. If vectored interrupt mode is not enabled, all interrupts will go to the general interrupt vector. To enable vectored interrupt mode, I need to set bit 23 of the cause register. I first read the cause register into the T0 register using the move from coprocessor 0 instruction. Then the next two instructions will set bit 23 in the T0 register by first moving a 1 to the T1 register and then use the insert instruction, inserting the first bit of register T1 into bit 23 of register T0. Now that the bit is set, I will write the value back to the cause register using the move to coprocessor 0 instruction. I'll use the EHB instruction to clear any hazard barrier that could exist with the write to the cause register. I need to make sure I don't get any watch point interrupts, so I want to make sure the watch registers are clear. I do this by moving register 0, which always has a value of 0, to the watch registers using the move to coprocessor 0 instruction. You can set the vector spacing between the interrupt vectors to suit your needs from no space, which is usually not desirable because all you could do is fall into the next vector, to 512 bytes, where you might place a complete interrupt routine. I'm going to set it for a maximum of 512 bytes. First, I read the interrupt control register into the T0 register using the move from coprocessor 0 instruction. The next two instructions will clear the vector spacing bits 5 through 9 in the T0 register. Now I will set the vector spacing. Notice how the register is laid out, so you can set the lower bits to the actual spacing you want. So all I have to do is OR in the spacing value into the T0 register. Then I just move the register T0 back to the interrupt control register using the move to coprocessor 0 instruction. In one of the examples, I will be using a shadow register set, so I need to configure which register set will be used by that interrupt vector. I want hardware interrupt 1 to use shadow register set 1. Hardware interrupt 1 goes to interrupt vector 3, since the first two interrupt vectors 0 and 1 are for software interrupts. Each field in the shadow register set map register is 4 bits. Each contains a number of the register set to be used, with 0 indicating the general purpose register set and a 1 through 15 indicating a shadow register set. Note, Most of our cores only allow 4 shadow register sets, so some of the values will be illegal. You can check how many shadow register sets a core has by reading the HSS field in the Shadow Register Set Control Register. In this example, only one vector will be using a shadow register set, so I can just write the number of shadow register sets to the correct field and set the rest to 0. I do this by setting bit 12 of register T1, which is effectively writes a 1 to the SSV3, so vector 3 will use shadow register set 1 and the rest will use the general purpose registers. I then move this value to the shadow register set map register using the move to coprocessor 0 instruction. Before we can call a C function, I need to set up the stack and global pointer registers. The stack and global data areas are allocated in the linker file, and the variables _stack top and GP point to the starting address of each section, so all I need to do is copy their values to registers. I do this with the load address instruction. In C, uninitialized variables are defined to be 0, so before I can jump to any code, I will need to initialize the uninitialized variable section BSS to 0. There are 2 variables defined in the linker file that help me do this. The first is the _FBSS, which points to the first address in the BSS section. Then, to find the end of the section, there is a variable simply called end, which actually points to the start of the next section. So to find the end address of the BSS section, I will need to subtract 4 bytes from it. I use the load address instruction to load these pointers into registers. I will just subtract the 2 registers to get the size of the BSS section. I check the size to see if the BSS section exists and will branch to the end of the code if the section is 0, indicating that there is no BSS data. Next is a short loop that uses the 0 register to clear each word in the BSS section. It loops by testing the current address stored in the T0 register to the end address stored in the T1 register and loops until the addresses match. I will use the branch delay slot to increment the current address. Since I intend to use a shadow register set, I need to initialize that set with the interrupt stack and global pointers. I can do this with the use of the write to GPR in previous shadow register set instruction. Before I can use the WRP GPR instruction, I must set the previous shadow register set field in the shadow register set control register with the number of the shadow register set I want to write to. To do this, I move the current value of the shadow register set control register to the T1 register using the move from coprocessor 0 instruction. I now will insert a 1 into the previous shadow register set field. I will then write the change back to the shadow register set control register with a move to coprocessor 0 instruction, and use the execution hazard barrier instruction to ensure the register write has taken to effect. Now I am ready to write to shadow register set 1. The interrupt stack, like the regular stack, is allocated by the linker file. The variable _int stack top is defined in the linker file and points to the top of the stack. I use the load address instruction to load it into the T1 register. I now load the shadow register set with the interrupt stack pointer and the global pointer. I am going to utilize the count and compare registers to generate an interrupt, so I need to set them to their initial values. I set the count register to 0 and I set the compare register to 512. The count register increments with each clock, and when it reaches the value in the compare register, a timer interrupt will happen. Setting the compare register to 512 should be enough time to jump to the main function and get our program started. We are almost to the point where we can call the C function main. I will enable all interrupts by clearing the ERL and EXL bit and setting the interrupt enable bits in the status register, and set the interrupt mask bits to 1 so all interrupt vectors will generate an interrupt. I will do this by moving the correct values to the status register. Now we can jump to the main function. I'll just use the load address instruction to load the address of main and then jump to main. Since I am done with the code section, I will turn reordering back on and use the .end directive so the linker will know that this is the end of the start function. At the end of the start.s file, I have added a linker directive to create two data sections. First, the C stack, and then the interrupt stack. This is done by declaring a section and then using the .space directive to give that section space in memory. Now for the interrupt functions themselves. I'm going to show you an interrupt function that will call a C function to do most of the work. In this example, there is not much to do, so the C function is very small, but it will serve as an example for how you would go about calling a C function from an interrupt routine. The first one I will go through is the non-shadow set version. As already covered in the assembly section of the training course, registers K0 and K1 are always free for an interrupt routine to use as long as the interrupts are disabled. I will use them in this interrupt routine to adjust the stack pointer. This function will continue to use the current stack to store registers and call a C function. To do this, I will need to allocate room on the stack for the registers I want to save. I use the stack pointer stored in the general purpose register SP, and since the stack grows downward, I will subtract the amount of stack space I need from the SP register. I also need to make sure that the pointer is aligned to a word boundary. Now that the stack is set up, I can start saving context. One note, there is 16 bytes that need to be available for C argument storage by C functions. So I will leave the first 16 bytes of the stack free, so the base register offset value for saving values to the stack will start at 20. I will use the store word instruction using the K1 register that has the adjusted stack pointer as a base register and increment offset values as I save the registers. I want to show you what you need to do to nest interrupts. To do this, there are some coprocessor 0 registers that need to be saved. Here I will read the value of the status register and the error program counter and save them to the stack. Before I allow nested interrupts, I need to reset the compare and count register. If I don't, I'll get this interrupt again when I enable interrupts. I reset the compare register by moving in a count value, and I clear the count register by moving the value in the 0 register to it. I am now ready to enable nested interrupts. To enable nested interrupts, I must clear the EXL bit of the status register. Register T1 holds the value of the status register, so I don't need to get it again, and since I have already saved the value to the stack, I can make changes to the T1 register. I use the insert instruction to insert a 0 into bit 1 of the register, which is the EXL bit, and move it back to the status register. One thing to note, you should also change the interrupt mask to mask out interrupts of equal and less than the priority level you are servicing. Last, I copy the stack pointer I have been using that is in the K1 register to the SP register and put an argument into the first argument register. The argument will be used in the C function to increment a counter in the global array. After the code returns from the called C function, I need to restore the state of the processor so it can continue processing whatever it was doing before being interrupted. I copy the stack pointer to K1 and use K1 as the base register to load the values from the stack. I'll restore the status register. Note, this also has the effect of disabling interrupts, since EXL should be set when the value was saved. Interrupts need to be disabled while we restore the rest of the registers. I'll restore the error PC, which has the address where processing will continue after the error return. Next, restore all the GPR registers. And last, use the error return instruction to atomically clear the EXL bit in the status register and return execution to the point before the interrupt. I'll now go through the code for hardware vector 1. Hardware vector 1 is set up with a shadow register set. Using the shadow register set is less overhead and makes it quicker to start servicing the interrupt, due to the fact that you do not need to save all the general purpose registers. I'll quickly go through the steps involved because they are very much the same as I have shown you for hardware vector 0, just a few less. First, you need to create a stack frame to save some of the registers and create an argument area before calling a C function. You need to save the status register and the error program counter to the stack, the same as before, but you don't need to save any other registers. Next, you need to reset the count and compare registers. Then you are ready to enable interrupts. Here I show the masking of the interrupt vector of the interrupt we are servicing. Once that is done, you can jump to the C function that will handle the rest of the interrupt processing. After the interrupt device has been serviced, restore the program counter and status register, reset the stack pointer, and return from the interrupt. I have created a Navigator ICS project, imported the interrupt example code to it, and built the example. If you need more information on how to do that, refer to the Navigator ICS training video. The example contains a simulator configuration file. The following fields in this file have been changed from their default values. Comment out the set app file line because the name of the application is supplied by Navigator ICS. Comment out the set trace file line because we won't need a trace file for this example. Set big endian to 0 because this example has been compiled for little endian. Change the set int lt _ip it to 2 for interrupt vector 2, which is connected to hardware interrupt vector 0. This will indicate to the simulator that it should loop the timer interrupt back to this vector. Change the timer interrupt enable to 1 to enable the use of the timer interrupt pin. And last, set shadow register sets to 1 to add a shadow register set to the core configuration. Now I will create a debug dialog. Be sure your project is selected in the Project Explorer pane. Go to the bug icon and select Open Debug Dialog. Now double-click on your project name that should be in the selection on the left-hand side. This will open a new debug dialog. Fill in the C and C++ application data by browsing to the project work directory and select main.el. Next, select the Debugger tab. In the Debug Configuration screen, select MIPSIM for the target interface. For the reset action, select No Reset. For the MIPSIM configuration file, browse to the Interrupt Project Working Directory and select the 4kec.cfg configuration file. For the target group, select 4ke cycle and make sure the target device is set to the 4ke LE for this example because it was built for Little Endian. Then select Debug. Select a breakpoint in the func1 function. Here I added the global variables to the variable window and ran to the breakpoint 10 times. I observed the loop count of 360. As you may recall, there are two interrupt routines, one for hardware vector 0 that we just ran, and one that uses a shadow register set for hardware vector 1. Now I want to run the interrupt function for hardware vector 1 to show you the difference in timing between the two. To do this, I need to change the simulator configuration file so the timer interrupt is looped back to interrupt vector 3, which is hardware vector 1. I do that and save the file and start another debug session. Now you can see the loop count has increased, indicating that there was more time to run normal code and therefore the interrupt took less time. In the previous run, the loop count was 360 loops per 10 interrupts. In this run, you can see the loop count increased to 403 per 10 interrupts. The CPU can also accommodate an external interrupt controller. In this mode, the 6 interrupt pins are interpreted as a 6-bit number. A 0 would indicate no interrupt pending, and that leaves 63 other values to serve as separate interrupt vectors. The external interrupt controller is a separate piece of logic supplied by the system. All interrupt pins from this device are connected to it. When a device raises an interrupt, this external interrupt controller must compare all interrupting devices with their programmed interrupt priority level and use the device with the highest priority as the interrupt source by presenting that device's interrupt priority level to the CPU. When the CPU gets this request, it will compare the requested interrupt priority level with the interrupt priority level you have programmed into the status register. If the requested priority level is higher than the interrupt priority level, the CPU writes this value to the RIPL field of the cause register and notifies the external interrupt controller that the request is being serviced. The RIPL is used as a vector number and the CPU begins to execute code at that vector. The shadow register set map register is not used in this mode. The mapping of the vectored interrupt to a shadow register set is done by designing the interrupt controller to provide the correct shadow register set number when the interrupt is requested. The CPU loads this shadow register set number into the shadow register set control register, making that shadow register set the current shadow register set when the interrupt processing starts. Vector spacing works the same as in vectored interrupt mode, and the interrupt routines and calling of C functions work the same. This ends the interrupt section. Thanks for watching.